Okay, so okay, now starting. Uh, Good afternoon, everybody. I don't know if you have a problem with my slides, please tell. And I'm supposing that everybody's getting these slides. Anyway, I'm gonna be publishing these slides on our Facebook page. Okay. So as I said before, this is the second class of the Renewable Energies and Energy Planning course, and I'm going to talk about the technical economic analysis of energy generation plants. And the importance of this subject is because of something that I said on the last class. One of the most important things, the most important concepts of last class was that fossil energy sources actually compete with renewable energy sources. Or, in other words, the displacement of fossil energy sources compete in a technical sense and also in an economical sense. Okay, so the idea today is to give you tools in order to understand this competition. If you're developing renewable sources, you must pay attention to these aspects. But also to give you these specific tools in terms of how to assess a project, an engineering project related to the production of some renewable energy carrier. It can be a biofuel, for instance, or bioelectricity. Okay, so this is the important concept of last week, and I'm gonna elaborate on this subject through an example. As I said, we're going to analyze an investment project in terms of its technical aspects, but mainly in terms of its economical aspects. And what we're going to do is what is called capital budgeting. Okay, so if you're interested in this subject, you're going to look for information on the internet. You can look for this expression here. Okay. Yeah, let's elaborate a little bit in terms of how an engineering project is developed. What are the procedures that lead to the decisions in the plural of an engineering project? First, you usually start by a conceptual project. So let's say I'm going to produce bioethanol from this type of residues, agricultural residues, at the rate of, let's say, 200 tons per hour. Then you make an analysis or some analysis, and after some decisions, you end up with an executive project. For those that are not familiar with the term, what I call an executive project is the whole project. If we're talking about a building, for instance, like this building that we are, the executive projects, you have the structural project, hydraulics, electrical installations. So it's the project detailed to the last bit of information in order that you can hire the construction of this project. Okay. So after you deal with these things, you are going to look at the economic sustainability of the project. That is, the success as a product and also as an investment project. Because let's say a refinery, a biorefinery, can be an excellent product in terms of producing the products that you want, let's say biofuels, chemical compounds, and some electricity. It can be able to produce that, but it's not economically viable. So it's a success as a product. I mean, the industrial installation that converts the feedstock into the products, but it may not be successful as an investment project. Okay, so if you decide that a project is both a success in terms of engineering performance and also in terms of economical performance, you start executing. So you implement, you build everything you must build, you commission the project, and you start operating, and that's when you start having revenues. So these ideas here belongs to what we call economic engineering, which is an application of technical economical analysis tools to the engineering project, aiming at identifying the best choice between excluding alternatives. What I'm going to do today is to give you some of these tools. So I'm going to be talking about, let's say, econometrics. These tools are means of measuring, assessing, attributing a number to the economical aspects of your project. And we're going to do this through an example, which I'm going to explain a little further. Yeah, right now. So we're going to do these things in terms of a case study. Okay, this case, we're going to decide. We're going to, let's say, we're going to pretend that we are, let's say, an investment group, and we need to invest R$1 billion in the renewable energy sector. Okay, let's say we are a pension fund. We have several types of investments, and one of our investments in our portfolio is to invest in renewable energy. Let's suppose that we're going to participate in one of those bids organized by the Brazilian government, for instance. Okay, so we want to invest R$1 billion, and we must decide if we're going to invest in photovoltaic energy or in wind energy. Okay, so that's the decision to be made. Okay, and an observation: both of these projects are greenfield projects. That means that there's nothing in the field. There's nothing, really nothing. We're going to build from the scratch a wind farm or a photovoltaic power plant. Okay. Another observation: this figure here does not refer to a photovoltaic power plant. It's actually a solar power plant. I just changed from the photovoltaic to the solar thermal plant because we're going to talk about solar electricity or thermal solar electricity in one of the future classes. Okay, just to remind that in terms of solar energy, you have the possibility of converting solar energy directly to electricity through photovoltaic panels, but also you convert solar energy into, let's say, heat, which will heat a working fluid, for instance, steam, which will be used to generate electricity. So that's not the case today. We're dealing with a photovoltaic power plant, a large-scale plant, and also a wind farm. So that's our case study, and the idea is to analyze these investment projects and to decide which project we're going to invest on. Okay, we're going to put our R$1 billion. In order to avoid all the engineering details, because that's the objective of other classes in the future, I'm going to, let's say, to use farmer projects, as I said, in order to avoid all the engineering details. Okay, for instance, what kind of turbine, wind turbine we're going to use. Well, I'm going to show you the different types of wind turbines, but very quickly today, there's going to be a specific class when I'm going to talk about wind turbines, and I'm going to give you all the details, and we're going to write down all the equations, and we're going to see that in a lot of details. Also, the same for photovoltaic. So, as I said, we're going to use projects, the characteristics of existing projects here in Brazil in what concerns the wind generation. So here in Brazil, I think I showed you a picture last week of the wind potential in the world. And the most interesting region in Brazil is Chapada do Araripe. I believe I explained you what's special about this region. Well, of course, you have a lot of wind, high intensity winds and regular winds, okay, a low turbulence level, but also the land value here is low, because if you're going to build wind farms on the coast, for instance, you compete with your investment project starts to compete with tourism project, for instance. So the idea here, actually, this is a semi-desertic area, so the price of the land here is very, very low. That's one advantage. And most of the Brazilian new wind farms are being constructed in this region. I listed some, okay, from some companies, Queiroz Galvão, I think you heard about that. And the most important one is Casa dos Ventos. Casa dos Ventos has, I think, the most installed capacity belongs to Casa dos Ventos. Okay, I listed some companies that have this type of project in Brazil. Okay, they participate in those bids for renewable energy. Okay, and when I say that I'm going to start from this known project is because we're not going to engineer anything. Okay, we're just going to make the choices that they made. Okay, as what in what concerns the photovoltaic power plant, I'm not going to use a Brazilian project. I'm going to use another one that I know near Berlin in Germany, because well, it has a very interesting story, and actually, it's not only about photovoltaics. I'm going to explain that, but the story starts before the Second World War. You know, Nazi Germany had a lot of airports belonging to Luftwaffe, and this area, after the reunification of Germany, was bought by a company that produced. This company, well, I think something's popping up here. Okay. This company, the core business of this company is to produce eggs, okay? And so they have to plant corn in order to produce the feedstock for the chickens, in order to produce these eggs. So they bought this area belonging to this airport, and the region, this region here was largely contaminated. Okay, so it was not adequate for agricultural production. So they had to decide what to do with this area here. So what they did, they constructed a photovoltaic power plant, because it's cheaper than discontaminating all this area, cleaning this area. You see the corn planted here, okay? And the contaminated area, they installed this photovoltaic power plant. But what's interesting about this project, as I said, it's not only about photovoltaics. Okay, so that's the architectural diagram of all the integration projects. Let's start here. You have the chicken here. They produce egg, and they also produce manure, excrements. Okay, so they take this feedstock, because it's very rich in nutrients. You mix with some corn, and you ferment that in order to produce. Yeah, well, does anybody else? Do you know the address? You type. Okay, can you send me the YouTube address? You just type. you just type my account, which is P Selegim here, and type live. You're gonna see my live channel. Okay. I'm there. Thank you. Okay. So there's a delay. Okay, between the. Okay. I think you're actually I think you're watching one of the old movies. Okay. Well, anyway, I'm gonna continue. Okay. So where was I? Yeah. You have these residues from which you produce biogas. Okay. And can I don't know? Can you turn off your mic, please? Yeah. Okay. Thanks. So you also have photovoltaics in that contaminated area, and the advantage of mixing photovoltaics with electricity from biogas is that the intermittency of the photovoltaic generation is compensated by the production of electricity from biogas. Okay, that's a very important aspect because biogas is a very stable means of producing electricity. Okay, and the sun, you know, it's not. So you during the night, you know, you're not going to generate, but even during the day, you may have a very cloudy day and the generation drops to almost zero. So you have to do something in order to compensate for these intermittencies. And one way of doing that is combining the electricity produced from biogas. This is a very interesting way of doing that. But further on, you know, the gas is transformed into electricity that was through an internal combustion engine, but also the residues from the fermenter here are used as fertilizer. Actually, the liquid part is sprayed in the fields, in their own fields, and the solid part is sold as a fertilizer. So this project, it's a very interesting project because it integrates a traditional agricultural activity, chickens and corn, but also you combine that with energy generation. I forgot to tell about the residual heat from the combustion engine is also sent as heating heat for the buildings of the town nearby this place. Okay, so we're going to take their project, their photovoltaic configuration, and we're going to use that in our case, the case study that we are developing here. Okay, this is a picture of this project. You see the solar panels here. The solar panels are fixed, which means that they are very cheap, but they are less efficient in terms of converting solar energy into electricity. One interesting stuff is that after the Second World War, this airport became a Soviet MiG base. So you see the bunkers here behind the solar panels. Well, these bunkers used to have MiGs, you know, the fighter plane. Today you see barbed wire and all this equipment for this farm, actually. Okay, and the hangars they use here, the buildings they use they are using for the magazine of these solid residues or fertilizer. Okay, so we're going to use the configuration, the engineering aspects of this project here, as I said, in order to avoid all the engineering. Okay, we're not going to make any engineering calculations today. Okay, so let's see. Just to remind what we have to do, we have to decide where to invest 1 billion in photovoltaic power plant or in a wind farm. Okay, so the decision process will follow more or less the following. We have to invest 1 billion. Okay, this money we're going to spend in capital. We're going to buy the wind turbines and so on. So that's the origin of the term capex. So it's capital for expenditure. Okay, and from this investment, this is also an important concept. From this investment, it is expected to have some revenues because, as I said, we are an investment fund or a pension fund, and we're going to use these revenues in order to pay our pensions, for instance. So we expect to have some revenue. Okay, but we always have an alternative. Okay, we are going to invest in photovoltaics or power plant. Excuse me, let me just turn off my Dropbox because it's always synchronizing here. Sorry for that. Okay. So as I was saying, we always have an alternative. Instead of investing in a risky investment, a photovoltaic or a wind farm, we could acquire, for instance, government bonds or another very low risk investments. And this alternative actually will bring about the concept of opportunity cost. So that's why I'm highlighting this alternative right now, but I'm not going to elaborate right now. The idea is that instead of investing in a power plant, we always can make one of those very low risk investments. So this will bring about the concept of opportunity cost. Okay, moving further, what we need to do in order to decide which investment to put our money is to construct a financial temporal simulation of the power plant, including expenditures occurring at the design and execution phases. Okay, so everything that you're going to spend before commissioning, you're going to include in this calculation, as well as the revenues and costs during the operation phase of the entire lifespan of our power plant. Okay, so we're going to do a financial simulation. And from this financial simulation, we're going to construct these econometric parameters, which will help us decide where to invest. Okay, so what we need to do is to simulate the project's cash flow. Okay, in Portuguese, sometimes I'm going to give you the terms in Portuguese just to be sure that you know what I'm talking about. So cash flow in Portuguese, fluxo de caixa. Okay, and that's what we do. We're going to capital budgeting. Okay, this cash flow. Just to give you some examples of what I said about starting from projects that are already commissioned, okay, in Brazil or in Germany. For instance, this is an example of the executive project of a wind farm, actually in Ethiopia, and that means that you have all the engineering aspects, but also all the economic aspects. This is, for instance, all the equipment and services that you're going to need for your project, for your wind farm, with all costs itemized here. See, so I don't know if you can read here the FOB price of turbines. Okay, the crane necessary to mount the generation on top of the generator on top of the tower, and so on and so forth. So you arrive at this kind of list, very extensive and detailed list, after starting from the conceptual project. Then you make all the preliminary engineering calculations, then you make the more detailed engineering calculations. So you have all the executive project, and then you can start by looking at what the costs. How much is going to cost to build a road to have access to the place where you're going to build the power plant, the wind power plant. Okay, so that's just an example because we're going to start from this type of information. Okay, so by cash flow analysis, what is cash flow analysis? So it's simply a graph showing all the expenses and incomes in function of the time. Okay, the convention here actually, what positive means income. Okay, so income is positive and an expense is negative, just a convention. Okay, so during the commissioning, during the implementation of the project, we are going to spend our capex. Okay, so where we build roads, we buy the power generators and so on and so forth, and this is represented by these arrows here. Okay, so the time period here can be a day, a month, a week. That's not important right now. The other type of element of the cash flow is the revenues. The idea is that after commissioning the project, you start producing electricity, you start to sell electricity, so you start to have incomes. So that's why I'm representing in positive here. Okay. Another element, and I erased all the arrows in order to not to pollute the slide. Okay, you have fixed costs. Fixed costs. The concept of fixed cost is a cost that is not influenced by the fact that you're having revenues, the fact that you're producing your products. Fixed cost can be something like if you rent a building to install your offices, for instance, this rent that you have to pay every month does not depend on the fact that you are producing or not electricity. So it's a fixed cost. It will happen no matter what. It will be present no matter what. Okay, but you also have operation costs, the OPEX. Okay, operation expenditures. So they are somehow influenced by the production. If you produce electricity, you have OPEX. If you do not, you don't have, or you have less. Okay, and let me see the next slide. Okay, and another aspect of the OPEX, I don't know if you can see here. Let me erase and get my pen. I um, I I try to represent an increasing cost in terms of time, in function of the time. Why is that? Because for several reasons, but for instance, your maintenance costs tend to increase with time because, well, your equipment becomes older and older, so you're going to expend more and more in order to keep this equipment working. It's like a car that you have to maintain the car, and the older the car is, the more you expend. Okay, so we're going to take that into account in our cash flow analysis somehow. Okay, so you can have other incomes and other expenses. The idea here is that you have to take everyone into account. Okay, so after integrating these, I'm going back one slide. After integrating all these curves, all these costs, you have the accumulated cash flow, which is roughly represented by this black curve here. It's a very typical cash flow curve, okay, of this type of project. The idea we're going to analyze this curve, okay. So we're going to work we're going to try to build a cash flow curve, accumulated cash flow curve for our wind farm and also for our photovoltaic power plant. So the idea, if you're not familiar with this concept, is like having a box of money. We have 1 billion reais in a box, in a cardboard box, and we start expending this money here during this period here, okay? And then we spend everything, or 1 billion reais, and the power plant is ready, it starts to work, so we start generating electricity, start having revenues. So you have money going back to the box, okay? So you have money going back to the box, and so on and so forth. I'm going to describe this curve. We're going to construct some geometric parameters for this curve, which are related to economical aspects, okay? So I listed a few here. I'm going to describe them. First, let's start by this concept here, the death valley. This is a very common and dramatic expression because it's really dramatic. The death valley is a period in which you already spent all your money. So you expend 1 billion reais and your box is empty, and you just wait and pray that you're going to have your money back. So you're going to have, after commissioning the power plant, the money is going to start flowing back to the box. Okay, so it's a dramatic period during a project because of several things that I'm going to explain right now. Okay, one of those things that contribute to the dramatic aspect of this expression is the possibility that your project is not a success. Why this can happen? Let's say that you bought a number of equipment, let's say wind turbines, with a new technology, very different from the usual, and you find out that this technology is not suited for the types of wind that you have in your power plant. So what you're going to have is you're going to have less electricity generation, so less revenues. And your curve, your cash flow, instead of following this, let's say, theoretical or path, it's going to follow, for instance, this path, this trajectory here. Okay, so that means that money is going back to the box, but at a very, very small rate, or smaller rate than you expected. So that means that your project is not a success, and you try to do something, you sue, for instance, your supplier, and they agree to change the wind turbines. Okay, so after you solving all the problems, then you start following the expected cash flow path. Okay, so the six. Wait. Okay, somebody.
Question. I have a question.
What?
And the question is, why is it that in the developing countries, most government or public funded projects rarely come out of the face value? Do you have any?
Sorry, I cannot hear you. Can you repeat your question, please?
Okay, the question is, I mean, in the developing countries, why do you have any reason why most public funded projects hardly come out of that value?
Yeah, I have an idea. I'm going to write it down here. Bad engineering. Okay, engineering, uh, engineering, and bad spelling. Okay, but also bad planning and so on. Okay, this is a possibility. Okay, I'm going to erase that because we are not used to this type of things. That's one possible reason. Okay. I don't know if I answer your question. Okay?
Uh, yes, but it's a bad planning. Because I remember that before they embark on this kind of project, they usually work with consultants
Uh-huh.
who usually how come bad planning is the case?
Yeah, for instance, let's say that you're a new company, so you're going to hire people to run your wind farm, for instance. Okay? What kind of people are you going to hire? You have to hire technicians that are very proficient in terms of wind technology. But you can, for some reason, hire people from the sugarcane industry. I don't know why. Huh? And what do you think will happen? These people that are not proficient or not used to this type of technology will make decisions during the commissioning or even before commissioning that will affect the performance of your project. So that's a possible reason, and I know this happens a lot in Brazil because we are deficient in terms of human resources. Okay, that's one problem that we have here. Okay,
Okay, thank
okay,
you.
okay. So moving forward, let's see. I talked about the Death Valley, the success of the project. Let's say that we are following the expected path. Another important point is this point here. This point means that all the money that you expend already is already back in your box. So you could even take this box and start investing, thinking about investing in some other things. So this point here represents the, the success of your investment project. This point means that you invested 1 billion reais and you got back 1 billion reais. What comes next is going to be profit. Is the money that you're going to use to pay your pensions, for instance, or I don't know. That's not important here. But all this area here, well, this area here, are the benefits of having invested in this particular project. Okay, but moving further, another important aspects is what we call the beginning of the senescence of the project. You see, because I'm going back a few slides, because your operating costs tends to increase during time, the revenue, the rate of revenue tends to decrease during time. Okay, so when this when the derivative here, actually, let me erase some of this. Uh, the derivative here starts to decrease, and after a certain limit, you may decide to do something to retrofit your installation, or simply to shut everything down and move, try to do another thing. Okay. As I said, this is due to the increase in operation costs, and then you have the end of the project, the end of the lifespan of the project. If I'm not mistaken, we're going to use 35 years. Okay, so our cash flow simulation is going to last for 35 years. Okay, uh, another important aspects. I made it in another slide in order to have a more clear view of these aspects. Is the benefit, this is positive, in the cost. So the relation between benefit and cost is another econometric parameter that we're going to calculate, but also what we call payback. Okay. Wait,
Professor,
go ahead.
um, I have a question. You mentioned now that the cash flow simulation is expected to last 35 years, right?
Yeah.
Is it depending on the project or for every project?
Yeah, you usually try to assess that. Okay, so in our case here, we are arbitrating 35 years. Okay, you actually, what you can do when if you observe that, sorry, if you observe that your operation costs are increasing too much, you can, for instance, expend some money and to have this, for instance. You can, for instance, let's say, change your wind turbine. You replace the whole turbine. So you expend some money and you have an increased uh, revenue here. But those more complex situations, I'm not going to simulate because they do not have more information than what I'm showing here. Okay, so you can have several types of different situations, uh, but I'm not going to show you here. About your questions, that yes, to be more explicit, we must decide the lifespan of the project. What I'm telling you is that you can increase this lifespan for some reason or not. Okay, if it's not, if it's a very old technology that you bought here, it's not interesting. It may be more interesting if you just shut everything down and build from scratch again. Okay. Okay. So I was talking about another important. Okay, I was talking about another important concept is the payback time. The payback time is the time period when you have your investment capital back. Okay. Uh, This is a very important parameter, and I'm going to give you some examples in a few minutes. I just want to talk about another important concept, the so-called break-even point, which is not applicable to our case here. Okay, so I'm just talk a little bit about the break-even, just for you to have an idea, a rough idea of this concept. But it's not, as I said, it's not applicable to this example. The break-even point, let's say that, let's suppose, or let's pretend that we are a car manufacturing company, okay, like GM or Ford or Fiat, okay. So we decide to produce a new car, a new model, okay. So we invest, we develop the car. We developed all the production line of this car, okay, and so we expend our 1 billion reais doing that, to developing the car, the, the beautiful aspects of the car, but also the machines that are going to produce the car, also the maintenance program of this car, and so on, okay. So we invested 1 billion reais, and we have a new car which is right now on the market. Uh, and we expect to have our money back, our 1 billion reais, let's say in 5 years. So the break-even point is the number of cars that you have to sell every month in order to in order to have a payback in 3 years. Okay, because if you sell, let's say, if you are fit and if you sell one car a month, that's a tragedy. Okay, if you sell 100 cars a month or 1,000 cars a month, that's quite all right. If you sell 10,000 cars a month, that's very good. Okay, so the break-even point is the number of cars that you have to sell, the number of units produced in order to achieve the expected payback. Okay, so this is not applicable to our case because the energy, that's a particularity of our system here in Brazil, is that this project, implicitly, I'm thinking about selling energy in one of those bids organized by the government agencies. So we sell all 35 years of electricity in one single bid, or you can sell 15 years or 10 years, but the fact is that the electricity, your products, is already sold. So you don't have to worry about, you only have to deliver that kind of electricity, that amount of electricity, but you don't have to worry about how much units, how many units of energy you have to produce in order to achieve the expected payback. Okay? So,
Professor,
yeah,
I have a question.
yeah, go ahead. Okay.
Yes, I don't understand why the break-even is not at the same level as the investment. I would imagine that the money you invest and then you get the payback at the same level. Why is it higher the maximum investment than the money you are investing?
Okay.
You have some proceeds. Do you know what I'm saying? In the graph, I'm looking at the graph,
Yeah.
and I will imagine that the break-even point would be at the starting point of the line, of the
Yeah,
right
yeah,
way.
yeah, yeah. That's not. That's just the way that I made the slide. The break even is not, as I said, does not mean anything in this type of project. A break even, actually, it could be something like this. In this, if I was going to make a cash flow for the car project, it should be something like this. Uh, let's say here we are selling, I don't know, 100 cars every month, so we achieve the expected payback. So it starts here, as you said. Okay, if we sell only one car, let's say one car, car a month. This line here is only one car a month. Okay, so the payback cannot be seen in this picture. It influences the path, the trajectory of the cash flow. Did you understand? Okay, I just wrote it here in this place in the slide just to remind myself of talking a little bit about the concept of break-even. Okay, I don't know.
Okay, yeah, I get the general idea.
Did you get? Okay. So
Yes, thank you.
let's see. Yeah, yeah. In the last parameter here is the relation between benefit and cost. We're going to talk a little bit about that. Okay. So yeah. And another comment before moving further, moving to our specific project. Another comment is that during the analysis of the project, you always have alternatives, as I said. Uh, let's say our case supposes that we're going to spend 1 billion reais. But suppose that during the analysis, one of your suppliers offers a more expensive equipment. As for instance, suppose that we are talking about a sugarcane mill. A typical sugarcane mill produces 50 megawatts. Okay, that's the surplus that you can sell on the grid. But during all the analysis, your supplier tells you that, oh, I'm now starting to sell a higher pressure boiler, 150 bar boiler. It's more expensive, so that means that instead of expending 1 billion reais, you're going to expend 1 billion 200 million, for instance. No, not that. Let's say 1 billion, yeah, 1 billion 50 million reais. So you're expending more than 1 billion reais, but the higher pressure boiler is more efficient. That means that it produces more electricity from the same amount of feedstock, in this case sugarcane bagasse. Okay, so if you have more electricity, let's suppose 60 megawatts instead of 50 megawatts, that means that your revenue is higher. Okay, so you always have this kind of situation. You may go back to the board of your investment fund and ask for 50 million more because it may be very advantageous, as I'm saying here. Okay, so that's a possibility that we're not going to consider here. Okay, but it's very true. It happens very frequently. Okay, so the idea now is to decide which one is better, a wind farm or a photovoltaic power plant. What we're going to do, we're going to build both cash flow, both cash flows, and from these cash flows, from the characteristics of these cash flows, we're going to decide which one is better. Okay, so that's the whole idea of this class today. Let's look at the aspects that are translated into numbers. Okay, for instance, let's start talking about the payback. The payback expresses the liquidity of your investment or the amount of exposure to risks. Okay, to understand that, let's suppose that you have 1 billion reais and you're going to build a wind farm you're going to build a wind farm, but you have not decided where to build this wind farm. So let's say that you're going to build this wind farm in Switzerland, okay? Or the alternative is to build a wind farm in, let's say, Venezuela, okay? So if you're going to build in Switzerland, there's no problem in having a very long payback period. Why? Because the country is very stable, so you can sacrifice the payback if in favor of other interesting aspects that your investment may present. Okay, but if you're going to invest in a very, let's say, risky scenario, like Venezuela, for instance, you would probably want to prioritize the amount of time that you are exposed to risks. That means that you're going to prioritize the payback. The lesser the payback time, the better. Why? Because you have your money back. If something happens, at least you have your 1 billion reais back. Okay, so that's the idea of the payback. It expresses, it quantifies the liquidity or the amount of risk that you're running during your project. Okay, but it also has disadvantages. For instance, it disregards the revenues after payback. Your project may be like this, or let me draw something here. Your project may be like this, or it may be like this. For some reason, after payback, the amount of revenue is very low. So the payback is okay, but what you get after the payback period is very low. Okay. It also disregards the temporal value of money. This is a very important concept, which I'm going to elaborate in a few minutes. The temporal value of money. Okay. Before talking about the temporal value of money, let's look at another parameter, the relation between benefit and cost. Okay, it expresses how much benefit can be obtained from each unit of value invested. Okay, so after doing all the calculations, you arrive at the conclusion that you have 20 cents of profit for every real invested, every unit of value. This is an interesting aspect. Okay, it's very simple. But let's talk about, yeah.
Professor, you made a comment that disregard revenue are talking about. Why should we disregard? Why should the revenue be disregarded?
No, I'm not saying that it should be disregarded. I'm saying that the parameter, the payback, for instance, 36 months, okay, it's a time period. 36 months, it's better than 48 months. That means that in 36 months, you have all the money in your box again. Okay, that's the only aspect that is assessed through this parameter here. If you want to quantify, if you want to analyze the revenues after payback, you have to use another parameter. Okay, that's what I'm saying. Okay, this parameter actually is related to this concept here, the temporal value of money. Okay, and so I'm going to elaborate on that right now, and it will lead us to the so-called internal rate of return, IRR. Okay, that's the name of this econometric parameter, internal rate of return. So let's talk about temporal value of money. I have to explain the concept before showing you how to calculate the internal rate of return. Okay, it's more important. I could show you the formulas and say, well, this is the internal rate of return. It's more is better, less is not so good, but you don't have the concept. The more important, it's not the number, is the concept behind the number. Because after all, at the end of the day, you're going to have to decide. And to decide, you have to know, you have to be very aware of all the concepts behind these parameters, these econometric parameters, okay? Okay, so to explain the concept, let me put you a situation. We have, let's say, two projects, project A and project B. Okay, the cash flow of the project A is something like that. And both projects, we're going to expend 100 reais. Okay, let me erase, I'm polluting too much my slide. Okay, so in both projects, are going to spend 100 reais. But in project A, in the first year, we get 0. In the second year, we get 55. In the third year, 50. And then nothing. Okay, sorry, just an observation. I try to translate everything in English, but sometimes I see that there are some things in Portuguese. Sorry for that. Okay, so if you look at the cash flow of project A and you make the calculations, you invested 100, and in 3 years you get 150. Okay, project B, on the other hand, you invest 100, first year 0, second year 20, third year 30, fourth year 70, and then 0. Okay, so project B, after doing all the calculations, the net values, you invested 100 and you got 20, but after 4 years. So which is better? To decide that, you have to answer Homer Simpson's question, which is to have a return of 15 in 3 years or to have 20 in 4 years. Or another way of putting is to have less profit right now or in a short period of time, or to have more profit in a longer time. That's the point. Okay. Do you have any idea of how to answer this question? It will depend actually in several aspects. For instance, the exposure to risk also, but also in remember, right in the beginning of the class, I told you that we always have alternatives. Instead of investing in A or B, we could buy government bonds, for instance, because you know all projects, all investments are subjected to risks. Yeah, even the government bonds are subjected to risks, but in principle they are very, very low risk. Okay, so let's elaborate on that. Or alternative, instead of investing in project A or investing in project B, we could, as I said, buy government bonds, like a very, very safe bonds, like for instance the United States of America debts. Okay, so if you could read the small letters here, you could read that, you could conclude that, well, it says that after a certain amount of years, 30 years, let's say, you're gonna get your money back, this amount of money, with an interest rate of, I don't know, it was 0% actually some time ago. Okay, let's just for the sake of simplicity fix our reference rate at 5% per year. Okay, so this represents the alternative. Instead, let me go back one slide. Instead of investing in A or investing in B, I could buy one of those bonds and have 5% of interest every year. Okay, so what would happen with our investment? We start with 100 reais. After 1 year, we multiply by 1.05. We had 105 reais. After the second year, we have 110 and 25. And after the third year, we have 115.76 reais. Okay, this is 5% every year. So instead, let me emphasize this. Instead of investing in A and B, we could have had this cash flow here. Okay, this is the cash flow of our reference investment. Okay, the problem is that we have to decide today and not in 3 years. Okay, so what we have to do is the contrary. We have to, instead of correcting our values to the future, we have to correct our future values to the past. Okay, so let's see how we do this from the past to the future. Actually, this is a geometric progression. Okay, so you have a future value calculated in terms of the present value. So multiplying by the reference rate here. And N stands for the number of periods. Okay, so PV is the present value, FV is the future value, and this coefficient here is the progressions coefficient, actually, and R is our reference rate. Okay, as I said, we have to decide today, so we have to, instead of transforming our present value into a future value, we have to do the opposite. We have to calculate the present value from the future values. So what we have to do, we invert this formula. Okay, so let's suppose we start from saying 100 reais in 3 years, and we go back. So we, instead of multiplying by 1.05, we divide by 1.05. Okay, so that's also a progression, a geometric progression, and the formula is here. Actually, this formula here you can obtain from this one, just simply by dividing everything by 1.1 plus r to the nth power. Okay, I'm trying to emphasize on the concepts, not on the formulas. So we could calculate all, we could correct all future values. We could bring all future values to the present and make all the calculations. We're going to do that. And we're going to calculate the net present value. Okay, NPV stands for net present value, which is the sum of all present values. I don't know if you understood the concept. What we're going to take, what we're going to do, we're going to transform all future values. For instance, this R5 here, we're going to send it back to the past, or to the present actually, send it back to the present by correcting, by applying this formula here, okay? And n is the number of periods. Okay? After adding expenses and incomes, we can calculate the net present value. Is this okay? So, are all the incomes, these are the expenses at the kth period of time. It may be a year or a week or a month, no problem. And R is the reference rate, or also called the discount rate, reflecting the opportunity cost. This is the important concept I was talking about, the opportunity cost, because when we decided to invest in A or B, they are exclusive, we did not invest in government bonds. So this has to be quantified. We have to access that. Ok. Tá tocando o tempo todo. Ah, deixa comigo, eu ignoro. É só fazer o quê? É só clicar aqui e ignorar. Tá bom.
Porque é um computador que tá aqui e tá lá também.
Ah, é? Tá bom, então. Obrigado. So, okay. Moving further, the opportunity cost, as I was saying, it represents the opportunity that we lost of investing in a very or virtually low zero risk investment as these type of bonds. Okay. Okay, so let's go. Let's do the calculations for our example. This is project A, this is B. Here are the numbers without correcting for the future value of money. Okay, so remember, we started by investing 100, project A, then we have 55, 50, 0. The net amount is 15. It represents 15% of interest, or benefit to cost ratio. But if we consider time, if we consider the cost of opportunity, we must correct this value. So 55 becomes actually, in the present, today, right now, 58.96. 50 reais becomes 43.19. And the formula, the correction formula is shown there. Okay? So when we correct for the future value of money, which takes into account the opportunity cost, instead of having 15 reais of profit, actually we're having only 2.50 reais. Okay? In project B, we can do the same. We correct all the values, all the future values, we correct and send them back to the present. And we in project B, we thought we were having 20 reais in terms of profit, but actually we are having only 1.64. So it seems, I'm going back to Homer Simpson. Let me see where, here. It seemed that project B, we get more money even though we should wait more time. Okay, compared with project A. But correcting correcting the future values, which, as I said, represent the opportunity cost, we see that project B is not as attractive as it seemed in the first place. Okay, why is that? Because let's say the biggest amount of money actually comes in the fourth year. So we waited for 4 years to have 70 reais. And here you have the opportunity cost behind. That's why 70 is translated into a low value, a relatively low value of 57.59 reais. Okay. Another important observation here is that all these calculations are like this because, well, some way we fixed 5% as our reference rate. This 5%, remember, it comes from it's a way of assessing, it's a means of assessing the opportunity cost. Okay, what happens if we change this rate? Because, well, it's arbitrated. Okay, what happens if we change? Instead of 5%, for instance, what happens if we set 5.6? Instead of buying bonds from USA, we buy bonds from Japan, for instance. They are paying a little bit more. It's well, North Korea is playing jokes on them, so it's a little bit riskier than buying American bonds. So that's why they are paying more interest. So let's say 5.60% a year. In this case, investment A, okay, correcting all the values, you have only 0.75 reais, a profit of only 0.75, and project B actually is deficitary. Okay, you have losses. Sorry, you have losses. You have a prejudice of 30 cents in project B. Okay, so the point here is that well, the amount of interest, or how you set, how you decide what's going to be your reference rates, will affect the behavior of your economical project, or actually the net present value. Okay, 0.75 and minus 0.30 represents the net present value. Okay, it's in Portuguese here. Okay, but it's the net present value, which is calculated with the help of this formula here. Okay, so the net present value takes into account the opportunity cost, which in order to do so, you have to decide what's going to be your reference rates, okay, or your discount rates. But it also has limitations. I'm going to show you some, which I'm going to try to answer further on. Okay, let's say, just for the sake of reasoning, that project A, in project A you have an initial investment of 10 million, and you have a net present value. You make all the calculations, cash flow, and so on and so forth, and your net present value is 2 millions. Okay. In project B, instead of investing 10 millions, you have 2 billions as your initial investment. And after constructing your cash flow and calculating all those parameters, you have a net present value of 3 millions. If you only look at the net present value, 3 millions is better than 2 millions. So you would decide for project B. But there's something wrong here. Okay, you invested, I don't know, much more than 10 millions, only 10 millions, several orders of magnitude more. So there's something wrong. Okay, and well, you can see that this aspect here is assessed. You can have a feeling about this problem if you calculate the ratio between investment and benefit. Okay, and by benefit you can calculate the net present value. You can replace benefit by the net present value. Okay. Well, let me move a little bit further in order to, because we're going to arrive at the internal rate of return. Okay. And let me show you how we can do this. I said that we have to fix, somehow decide what's going to be our reference rates, this letter R here in this formula. Okay, I say that it represents our opportunity cost, but well, it's rather arbitrary, and we have to somehow decide. We have to put a number here based on some assumptions that we do. Okay, so what happens if we vary this number? Let's just play with the formula right now. Right now, I'm not interested in the concept. I'm interested in the behavior of the formula when we vary this number R here. Okay, so we're going to construct two functions, the net present value of project A in function of the discount rate, and the same thing for project B. Let's put this into a graph. So project A, the cash flow is here for project A and B, okay? And you have these curves here. You have the red one represents project B, the blue one represents project A. And you see that project B, the net present value of project B decreases faster than project A in function of your discount rate. I omitted here. Okay, here is R, and here is the net present value in function of R. Okay. So, and also there are two special numbers when your net present value is 0. Okay, is 5.9 for project A and 5.2 for project B. So what these curves represent in terms of cost of opportunity, but also in terms of robustness of the investment project. I'm going to elaborate on that. Suppose that we have an interest rate, or sorry, reference rates, a discount rate, as indicated by the dotted line. So if we have this discount rate, and if we consider project the net present value as our single decision parameter, well, in this case, project A is better than project B because the net present value of project A is greater than the net present value of project B. Okay. If we change that, if we have let's say a less costly opportunity cost, in this case project B, in this case R is smaller, okay, the discount rate is smaller. Let's say these are Japan bonds, and this is the USA bonds, okay. In this case project B is better than project A. Okay, so depending on the reference rate, you may decide for A or B. But there's another aspect that I want to show you, is the exposition to risk. Okay, so the point is how to evaluate the opportunity cost by setting the discount rate. How do we do that? Okay, oops, sorry. Because why this is important? Because you know the discount rates, the actual cost of opportunity may vary a lot during time. This, for instance, this is just an instance, an example. This is the equivalent of the Brazilian discount rate or reference rate, which is the so-called Selic. This is the variation of the Selic during the years from 1994 to today. It's 9.25, but you see during time it varied a lot. It went to astonishing 85% in 1995. Okay, this is during a period of very high inflation. So how can you, as I was saying, how can you set your discount rate in order to make these calculations and make the decision when you have this kind of situation? Very, very big variations in Brazil. If you do the same for the United States, it's a lot more stable. It's in the United States, it's something near zero here during all this time. Also Japan and so on. Okay, so what does this mean? What does it mean when you have zero net present value? Okay, that's the limit between having a profit and not having profit. Okay, so that's what we call the viability limit, the discount rate above which the project is no longer economically viable. So this number here, which zeros the net present value, represents the so-called viability limit, and the fact that the viability limit of project A is greater than the viability limit of project B tells us that project A is in some way or more robust than project B. I mean, for more robust, I mean it's still viable, it's still profitable, even if your discount rate, your actual discount rate, so your actual opportunity cost varies a lot during time. Okay, so project A is more robust than project B. Okay, so this number was baptized as internal rate of return. As I said, it represents the robustness of the project. And you can calculate the internal rate of return by zeroing the net present value in that formula. The formula that you use to calculate the net present value. And instead of or, you have this is in Portuguese, sorry. You have the internal rate of return here. In Portuguese is taxa interna de retorno. That's why it's written like that. Okay, I forgot to translate. Okay, so when you have a bigger internal rate of return, that means that your project is more robust or more resilient than your other alternative, your other project. Okay? Okay, so, well, there are other econometric parameters that we could use for this example. I'm not going to be extensive on that because I would have to, I would take several hours, and that's not the idea. The idea is that from your cash flow simulations, you construct numbers which represent some aspects of your project, some economical aspects. For instance, cost of opportunity. For instance, the temporal value of money, and so on and so forth. Okay, so the idea is to construct these parameters from your cash flow, based on your cash flow, and to decide to use these numbers to objectively decide between excluding alternatives. Okay, so let's go back to our case study, which was, remember, the technical economic analysis of an investment project, the capital budgeting of photovoltaic power plant in a wind farm. Okay, so the decision process, let's elaborate on that, is first we start from 1 billion reais. Sorry, we analyze both engineering projects, the wind farm and the photovoltaic. Let's, for the sake of simplicity, just consider this example here, the wind farm. So we make the engineering project, executive project, and so on. We calculate all economics, capex and opex. We generate the cash flow, and then we construct these decision parameters here, which serves as a basis for our decision. After deciding, we execute the project. But, you know, this doesn't need to be a linear process like this. In every level, you can go back and change something in order to improve your project. For instance, you can decide to change the type of turbine. It will change eventually the engineering project and also all economics and so on. So this project, this decision, this cycle may be repeated several times, and when you're done with this decision cycle, you finally decide and you execute your project. Okay? So that's the idea, that's what we're going to do. We're going to do one single cycle of this project for the wind farm and also for the photovoltaic power plant. But I'm going to give you some hints about what could be a second decision cycle. Okay, let's go. So let's see how it is done for our specific cases. The wind farm from the projects in Chapada do Araripe and the photovoltaic power plant from that company in Berlin. Okay, let's just a few slides about technology. Uh, starting with the wind technology. You see, in time, let me see. In time, you see that, well, what I want to show you here is that you have several different technologies. The most common ones are the horizontal axis turbines here. You see that they are increasing in size. The longer the blades, the more efficient the turbine is because of the vortexes that you have on the tip. Okay, so the tendency is to increase, and well, there are some limits. You cannot exceed more than, let's say, 100 meters onshore, basically because you cannot, it's very hard to transport your blade from the factory to the installation place. So that is related to the geometry of roads and lanes and streets. Okay, that's one of the reasons why wind farms are moving offshore, because offshore you can build, you have several advantages. You can build bigger blades, bigger turbines, so more efficient turbines. Yeah, well, you just use a crane on a boat here to construct these windmills, so you don't have a big problem. Now another interesting point is that the winds tend to be more regular offshore, more intense and more regular offshore than onshore, compared with winds onshore. Okay, and also let's say visual pollution and acoustic pollution. Okay, you have less problems offshore compared with onshore. Have you ever heard this term? Yes, sorry. Yes, but not in my backyard. Yes, but not in my backyard. This is it's not exactly a joke, but the wind technology is a very mature technology. Wind generation is a very mature technology, and it is so mature that people always say yes to wind technology, but they don't want these windmills on their backyards because of visual pollution and also because of noise. Okay, so that's one reason why windmills are being moved offshore. You also have several different technologies. You have, for instance, vertical axis turbines. They are less efficient in terms of converting wind energy into mechanical energy, but they generate less noise, so they are more adequate for urban applications. You have several technologies. I'm not going to show you all of them today, but we're going to have a specific day when we're going to analyze all these things. Another information in this slide is the tendency to decrease the capex associated with wind technology, with a wind turbine, due to incorporation of new technologies. And these new technologies are broke down here in terms of, let's say, better aerodynamics. You can gain 2% by having better aerodynamics, controls, and so on. Let's see. Well, the nacelle, the geometry of the nacelle, which is this, where you have all the equipment here, the supervisory system, and so on. So the idea is that the price will tend to decrease because of new technologies, and this actually is shown in more detail here. But also an actual curve. No? The price is dropping during time. Also, not only because of new technology, but also because of scale. The installed capacity is increasing, so that means that you can benefit from scale effects. Okay, so this is actually happening for wind turbines. And just an example now, how can we calculate the investment, the capital for expenditure in these technologies? Well, what I'm showing you here is just, let's say, just opening the door to this area, to this economic engineering. But this is an actual example. Okay, one way of assessing the amount of money that you will expend to construct your wind farm and also to operate your wind farm can be estimated like this. All of these dots are actually actual wind farms built in Brazil, but also in the United States, in Europe, and so on. Every dot, for every dot, you have a lot of information. You have the installed power, you have the technology, and so on, but also how much it costs and how much it costs to operate the corresponding project. So you list all this. This is a data gathering effort, actually. Okay, so after you're constructing this database, you can plot, for instance, the cost, how much it cost to build that specific power plant, and in terms of the installed power. The concept of installed power is the sum of all the powers of all windmills, the power of the generator. How much power it's going to generate will depend on the intensity of winds and so on. Okay, but that's the nominal power of the wind generators. Okay, after plotting all these points, you can calculate a tendency, and this number here represents what? Represents the cost in $1 million in terms of megawatts installed. Okay, so that's exactly what was done for one of those projects in Chapada do Araripe, actually. Okay, this is an actual example. And well, it's as simple as that. But the problem is to have all these points, to have all this information in a coherent manner. Okay. So the idea is, I'm not showing you all the calculations. The idea is to end up with a table like this. Well, this is PV is actually wind. Okay, this is wrong. This is wind. So the idea is to end up with this kind of table in which you have, for instance, your capex, your opex, and also another parameter here which represents the amount of money that you're going to make when you start selling electricity. Okay, I'm going to explain you that. But also these are economical parameters, but also some technical parameters. For instance, the efficiency of your power plant, the capacity factor. Okay, 35%. This means that uh, you're going to generate 35% of your installed power. Okay? And why is that? Because, well, winds are intermittent. So sometimes you have wind, sometimes you don't have wind. So in Chapada do Araripe, the capacity factor is 35%, which is a very good number compared to other other wind farms, other places in which you have wind farms. Okay? So the important numbers for today's analysis are the economical parameters, and also the capacity factor and the time necessary to build the wind farm, 18 months. Okay? Another aspect which I'm going to take into account is the depreciation, okay, of the equipment, in order to take into account the increase of cost due to maintenance, because your equipment is getting older. So we're going to take into account, that means that we're going to multiply this number, 7.21 reais per kilowatt installed per month, okay, per month, and we're going to multiply this number by an increasing number, an increasing function, a function that will increase with time, okay? Well, the calculations that we're going to make, this is just an example, is so we take our 1 billion reais, we spend that in a wind farm. So we have 310 megawatts peak, okay, in terms of installed power. Correcting for the capacity factor, that means that we're going to generate 108 megawatts. Those in the Brazilian term for that is the physical power or physical energy. Okay, so that's what you could expect to generate in 1 year. So this is it is very likely that you generate this amount of power in average during the year. So we transformed our capex into a wind farm. This, let me erase a few bits here. So we transform our capital into a wind farm. This wind farm installed in Chapada do Araripe will generate this average power during a year, which will generate 0.85 million reais every month, considering, let me go back just this, considering, sorry, let me erase, considering that we're going to get paid 120 reais for every megawatt hour, okay? So 108 megawatts will generate this income, okay? And this, also this average power will generate this type of cost due to operation of the power plant. Okay, sorry, it's the opposite. This is the cost. Okay, this is OPEX, and this is the revenues. Okay, and the calculations. Just an observation here. The units, we treat them as we treat in algebra. Okay, so we can cancel out hour with hour and so on. Just to show you the calculations here. Okay, so after that, we will start implementing our cash flow graph or cash flow table. Actually, we will build that in a spreadsheet, which I can make available to you through our Facebook page. Okay, so let's see. Let's construct our cash flow. Okay, we start by expanding our capex, or 1 billion reais in 18 months. So we're going to expand that here in 18 months. Okay, and an important observation here is we can choose to build our power plant in modules. Like here, we commission 1/3 of our power plant in 6 months. The second third of our power plant we commission in 12 months, and the third we commission in 18 months. Okay, why we do that? We do that to anticipate generation of income. Okay, in order to anticipate the payback of the project. I'm going to do that for the power plant, the wind farm, and also for the photovoltaics. Okay. So when we commission the first module of our power plant, we start having revenue, but also we have operation costs. Okay, and the same for the second module, and the same for the third module. And after the third module, we have the full income generation, 9.33 million reais every month, and with a cost of 0.85 million reais a month. Okay? To consider depreciation of the equipment, I'm going to multiply this function by something that will increase, okay, in order to take into account the fact that our equipment is getting old and we have to expend more and more money as the time passes. Okay, so I'm going to multiply that by a function f of t, which will represent this increase in our OPEX. Okay, I'm going to show you what this function is in the spreadsheet right here. Okay, so yeah.
Hello.
Yeah.
From the graph you showed, the revenue increases as the operational cost increases. Is it possible that the revenue will increase with lower operational costs in some cases?
Yeah, it is, but you could consider that. As I said, here in well, this is a specific case because in this case, this energy is sold in bids. So I'm going to show you, I think it's the last class, I'm going to show you the spreadsheets that the Brazilian agency publishes, in which you have all the information. So you can see things like company A bought energy from company B. So they bought, let's say, 100 megawatts every year during 50 years at the price stated in the contract. So in principle, the price that company B is paying company A is fixed at the bid, at the beginning of the contract. Okay, I'm disregarding completely inflation. If you want to consider inflation, it's just a complication because you have to multiply, you have to correct values, but there's no new information. Okay, so in this specific case, the price of energy is fixed a priori, so it's not going to change during the 35 years of your project. I'm saying that you can consider that, but you could also consider that your revenue could decrease during time. Okay?
Okay.
Okay? Well,
Okay.
okay. Okay. So this is the structure of our cash flow, and what we have to do is to implement that in a spreadsheet, which is done here. Okay, you see, this is the capital expenditure. Okay, the months is here. So the capital being spent from month 1 to month 18. Okay, so this column here represents this curve here. Okay, just to be very clear. The operation cost is written here. Okay, the first third, the second third, and the third here. Okay, those are the expenses. So this column here actually, oops, sorry, represents this curve here and the revenues. Okay, and this is the sum of all these cells actually. And here's the accumulated cash flow, which is represented here. Okay, so this spreadsheet I'm going to publish in the Facebook page, so you can download this sheet and see the wind farm project and also the photovoltaic power plant, the cash flows. But the point is that after constructing your cash flow curve, which is this column here, and this is the graphical representation of your cash flow. I forgot to explain about the depreciation curve. This function here, this f of t, is actually this function here. 1 plus d multiplied by n divided by capital N. Okay, n is the number of months, and capital N is the total duration of the of the um, of the project. Okay. I don't know if this is correct, but you're going to see this formula is implemented in this cell here. Okay, I think it's, yeah, that's correct. The parameter d, the bigger the parameter d, the more intense is the depreciation. Okay, and this parameter is fixed here, 5. The number 5 is this depreciation is this number d. Okay, well, so after constructing your cash flow, you're going to calculate all those econometric parameters. Okay, so we fixed a reference rate or a discount rate, 0.55 a month, and the net present value is 42 million reais. The internal return rate is 0.5 a month or 7.8 a year. Okay, and the relation between benefit and cost is 1.12, almost 1.13. An observation: the net present value and the internal return rate of return are actually built-in functions Excel that you call from Excel. Okay, so you don't have to worry to program all those not very complicated formula, but you know Murphy's law. When one thing can go wrong, it will go wrong. Okay, so you don't have to implement this formula. You simply use the built-in function from Excel's library. Okay, so those are the numbers for the wind farm. Let's see now the photovoltaic power plant. Before going to that, a little bit, some information about the technological aspects, just to show you. We're going to come back to this subject in the future. You know, you have several types of materials for these photovoltaic panels. You have flexible materials, which you can mount over curved surfaces, for instance. They are more interesting, but they are less efficient in terms of converting solar energy into electricity. You have rigid materials that are more efficient, but they are more fragile. So here you use the roof's structure to support the panels. They are flexible, they are resistant, so you don't have to worry about the structure. But for these materials that are more fragile, you have to worry about this the frame support, the supporting frame of these panels. Okay, so those are the types of decisions that you have to make. Are you going to buy this type of panels or these type of panels? You also have panels that follows the movement of the sun. Okay, track the movement of the sun. They are more expensive, but they are more efficient in compensation. Okay. Uh, Also, the price is decreasing during time because of scale effects. Okay, and another information, another thing that I wanted to comment is that you have the solar panels, but you also have to have other types of equipment. You have to have an inverter. Actually, the energy produced, the electrical current produced by these panels are continuous, so you have to transform that into an alternating current. So you have to use an inverter. Okay, you also have to have some backup system, because when you sell energy, you sell 24 hours of power, of electrical power. So during the night or during cloudy days, you are going to use your backup systems. Yeah? So your capex will be expanded not only in solar panels, but also in this type of equipment here. Okay, and the amount of money that you're going to spend, how can you evaluate that? That's the same. We're going to do the same thing that we did for the wind farm. So every dot here represents a photovoltaic solar power plant. Okay, so you plot the numbers, the cost of the power plant in terms of the installed power. And installed power means that if you have the sun on your solar panel, direct incidence, okay, at 12 o'clock in the equator, and in this situation, you're going to generate the installed power. The amount of energy arriving at your solar panel will vary during the day, so this will be taken into account through a capacity factor, the same way that we did for the wind turbine. Okay, so every point here represents a solar power plant. So you have all the information, how much it costs, to operate, and so on. And you, for instance, plot the cost, the capex associated with the installed power. You can calculate a tendency. So this number here represents the how much you million reais in terms of installed power in megawatts. Okay. The idea is the same, so you end up with a table with all your important parameters. The most important ones for today's class is the operating cost, the capex associated, and the price paid by the companies. Okay, I don't know if you remember. This is bigger than. I'm going back to the wind turbines table. Okay, excuse me for that. Here, you see, we were getting 120 reais per megawatt hour, and for the solar photovoltaic energy, we're getting 215 reais. Okay, keep this in mind, bear this in mind. I'm going to come back to this to explain this difference in a little while. Okay. Also, the operating cost will be increased, will be affected by depreciation as the same way we did for the wind farm. Okay. The calculations are the same. We expend a billion reais, and so we buy a photovoltaic power plant with 89 megawatts. This is installed power. P stands for peak. Okay, so 89%, 89 megawatts corrected by the capacity factor represents 27 megawatts, and this is an average power. This is what you really get during a year in average. Okay, and this number 30% actually comes. I forgot to show you. Comes from that's the capacity factor associated with Chapada do Araripe. Okay, this is much less in Germany, for instance. Okay, so 1 billion became 89 megawatts peak. 89 megawatts peak becomes 27 megawatts average. So this is what you sell on the market, 27 megawatts. The price that you get, you multiply that by the price that you get, you transform 27 megawatts into 4.18 million reais a month, and this will cost for you 0.18 million reais a month. This is operating cost. This is your revenue. Okay?
Professor?
Yeah, go ahead.
I have a question here. Why in the first line you have 89 megawatts and the second one is gigawatts? Is it a mistake or I didn't understand.
Just a mistake. Just a mistake.
Okay.
That's copy paste from this slide here. You see?
I see.
The same mistake here. That's why I was. Okay, sorry for that.
Okay, yeah, I just confused. Okay, thank you.
So moving further, 27 megawatts average will represent this monthly cost and this monthly revenue. Okay, the calculations are the same. So now we are ready to start building our cash flow. Okay, so everything is the same. We expend 1 billion reais in 36 months. It takes more time to implement a photovoltaic power plant, but we can slice it in more modules. I chose to slice it in 6 modules, hoping that this could compensate for the longer time to implement the power plant. Okay, and remember, this effort is to try to anticipate the payback. Okay, so the first module is commissioned in 6 months, 12 months, 18, 24, 30, 36. Okay, so we start having revenues after 6 months, and so we also have the expenses corresponding to the operation costs. Okay, the same story. The depreciation will be taken into account through a specific arbitrated function, actually. Okay, so this is the structure of our cash flow. This is the implementation of our cash flow. You see, this is our capex from month 1 to month 36. The operation costs, expenses, revenues, the instantaneous cash flow, and the accumulated cash flow. Okay, here. So this is the graph that you have. We use the same depreciation function, but the parameter D, which takes into account the intensity of the depreciation, is lower. I don't know if you remember, I'm going back a few slides. We chose a stronger depreciation here, 5, and you can see that the cash flow is slightly concave here, okay? And for the photovoltaic power plant, you see the number here is 2, so the depreciation is less intense, and you see no curvature here, okay? Well, anyway, once you have this column here, which is your cash flow, you calculate those econometric parameters. So I'm fixing the same discount rate, 0.54 a month. The net present value is negative, 401 million reais. The annual internal return rate is 2.75, and the relation benefit cost is 0.66. So you see that you already see that it's very, very non-attractive. Okay, negative present value means that your opportunity cost is too high. You would probably build this project in a place where your opportunity cost is not so high. Okay, but let's compare the two projects and try to decide which one is better. Okay, so let's see the numbers together. This is the accumulated cash flow for the wind farm, the accumulated cash flow for the photovoltaic power plant. Okay, and these are the numbers. First, the net present value, positive 42 million reais, and here is negative. So let's put a mark. So the better one is here. If we look only at the net present value, let's look at the internal return, the internal rate of return, 7.81 for the wind farm and 2.75 for the solar power plant. So the wind farm is better. Also, the relation between benefit and cost, well, the wind farm is better. Okay, so which would you decide? Obviously, the wind farm. Okay, so the decision would be wind. However, it will depend, it may depend in other aspects, depending if you are the investor or depending if you are government and so on and so forth. I'm going to try to give you some ideas about that. Okay. Remember, I'm going back a few slides, maybe a lot of slides. Sorry, let's going back here. Okay, so we are at this point. We calculated all the parameters, and it seems that the wind farm is better. But we can try to change things in order to make the photovoltaic power plant more attractive. So let's see what could be done and why this could be done. Why someone accepts paying more for photovoltaic electricity. Okay, the idea, for instance, is that if you are government, as federal government, for instance, and if you let these numbers in the market, every investor will decide for a wind farm. And after a certain period of time, you will have 100% of all these renewables invested in wind farms. So you don't, this is a fragile system because it's not diversified. So if you're government, you would like to diversify your energy sources, so you can create incentives in order to make other types of energy, and photovoltaics is one of them, more attractive. For instance, you can discount, you can waive some taxes that that these investments would pay for you. You can create differentiated tariffs, subsidies, and so on and so forth. So you do that because you have, let's say, a broader strategy, diversification of energy sources. Okay. Also, you know, I'm not. I didn't give you information about, but also from the investor's point of view, what interests is the amount of money that you have, that you get back from your investment, which you can use to, let's say, pay your pensions if we were a pension fund, for instance. But so it generates profit. Okay, so if you're an investor, you are interested in profit. If you are a government, you also want a profit for the investor because you have taxes associated with this profit, but you also want to generate jobs and to, let's say, to multiply this investment. So for instance, if we compare, the problem here is that we are comparing two power plants which they do not pay for the fuel. What is the fuel? The basic energy source of the power plant, of the wind farm, is wind, which is free. Also, sun is free, so you don't have to pay for the fuel of your power plant. But if the project, if our decision was between a wind farm and a sugar mill, for instance, okay, a sugar mill, or better than a sugar mill, if wind farm or biomass thermoelectric power plant, okay, and using, I don't know, eucalyptus, for instance, okay. So what is the fuel of the thermal power plant? Eucalyptus. And eucalyptus is not free. You have to grow eucalyptus, you have to plant, you have to grow, and you're going to pay for the eucalyptus. So the power plant, the thermal power plant, generates profit and stimulates the agricultural market around the power plant. You see? So the amount of development induced by the thermal power plant is bigger, is more significant than the amount of development generated, induced by those types of photovoltaics or a wind farm. So depending if you're an investor, government, or even the future employee of these power plants, the decision can be modular. Okay, so coming back to this example, you see this table here. This is just to show you that solar energy is really small compared to wind energy in Brazil. This is from the Balanço Energético Nacional, which is the national statistics on energy in Brazil, okay? Balanço Elétrico Nacional 2016. Balanço energético, né? Energetic, forgot the word. Balanço Energético Nacional 2016, okay? Just to show you that the amount of photovoltaics is really small, okay? It had a 13% of increase from 2015 to 2015, but it still depends on incentives and subsidies and so on. Wind energy is actually it is the fastest growing energy, not only in Brazil but also in the world. Okay, it's a very competitive type of energy. And well, thermal energy is increasing in Brazil due to a specific situation in the last period, in the last few years. Okay. So, well, this is what I had to say. Just since we have a few minutes, I just want to show you the spreadsheet and show you the influence of two things. Okay, the effect. Let me get the example here. No, not here. Ish. Sorry, just let me just find my spreadsheet. I know where it is. Estilisco, pontes, just a minute, please. Let me try to find my spreadsheet. No. Wait. Well, I don't know where is my spreadsheet, so I'm just going to explain what I wanted to show you. What I want you to do with this example. So let me just spend 5 minutes to explain something here. What I wanted you to do is I want you to download this spreadsheet. I'm going to find it. I'm going to publish the link on our Facebook page. And what I want you to do is to look at the formulas that were implemented here, and also try to change these numbers. For instance, you change the depreciation rate here. Okay, you can increase, decrease. Also, you change the discount rate. Let's say 0.5, 0.54 a month is like having a saving account here in Brazil. A saving account is a caderneta de poupança, ok? Uma aplicação, an investment in a poupança here in Brazil, okay? So 0.54 is like having a saving account. That's the tax paid here in Brazil, but suppose that you're not in Brazil, that you're in Germany. So the taxes in a country like Germany is a lot lower than that, 6% a year, 7% a year. So you try to put 0.2% as a discount rate and compare 0.2, the effect, and observe the effect that you have in these values. Okay, you will see that the net present value may become positive if you have smaller discount rates. So I want you to download this spreadsheet and try to play with these formulas, change, and try to, for instance, instead of implementing like this, you can change. You can, I don't know, try to implement in more modules to try to make the investment more attractive. Okay, just to give you a feeling of all these technical, economical aspects. Okay, and the last thing I wanted to say is that this is the only class in which I'm going to talk about economics. the following classes, I'm not going to talk, I'm not going to explain. We may use some of these parameters, but I'm not going to come back to this subject in the future, okay? We're going to focus on the engineering and scientific aspects of all these energy sources. And in the last class, I'm going to talk about energy planning, which is different than the economics of energy. Okay? Another observation, a few of you guys asked me about how I'm going to grade you guys. Actually, I'm going to ask, I'm not going to pass a test. I'm going to ask for you in the end of the course that you give me a text, huh? I don't know, 10 pages, 50, you choose. Um, Talking about one of the classes of the course. It can be this class, Technical Economic Analysis. It can be about transportation sector or solar energy. You choose which class you want to talk about, and you deliver a text, you write a report, okay? And I'm going to evaluate that and give you a grade based on that. Okay? Any more questions? Okay, so that's it. Thank you very much.
Teacher, thank you.
Thank you.
Thank you so much. Teacher,
Wait,
thank you.
go ahead. I forgot to say, if some of you guys want to ask me a question in Portuguese, no problem. Go ahead, ask in Portuguese. I will translate the question to English to be sure that everybody understand, and I will answer it in English. If any of you guys have a problem or some difficulties with English, please ask, okay? And if you want to ask questions in Portuguese, please do so. Okay? Thank you.
Okay, thank you. Thank you.